Hello. Hello.
Namaskar, respected Professor Bajrang Pani ji, Dean of Colleges, Professor Sanjeev, Dean Faculty of Law, Professor Rajiv Gupta, CEO IUE. We have Dean Science, Professor Devjyoti Chaudhary, Professor T. R. Seshadri, Professor A.K. Tandanji, faculty. Students of the program. Can I put the podium? Sorry for the disturbance in the sound, but is interrupting the whole process. So very warm welcome to each one of you to the celebration of National Space Day. We all know that National Space Day is being celebrated for the first time in India to commemorate last year, that is 23rd August, when India was able to make a soft landing on Moon, on the South Pole, by which India has become the 4th country for soft landing on Moon and the first country to land in the South Pole, which is a very challenging area. The achievement which India has made through that particular day by soft landing on Moon has kind of opened new vistas in space science, because through that we are able to study not just the surface and other elements which are present on Moon's surface, but also we got the knowledge and experience of landing in other planets, because we have, as we see, that ISRO has many plans of future for taking the exploration ahead to other planets, and we also know that we already have a mission towards studying the sun. If you look at history of India, we see that in ancient times, India was very strong in astronomy. I don't know how much we can say about the astrophysics discipline or domain in our Department of Physics, because of the fact that we have very few teachers who are specialized in astrophysics. But since I'm talking to BTech students, the technology students, and I'm sure that you'll be able to come up with many ideas which will definitely take ahead our exploration as well as our study in space science. if one look at, I was quite surprised when I found that there are two things which came across when we look at how in ancient India, in spite of not having technology to study the stars, how the rishis were able to say, find out that there were twin, stars by the name of Arundhati and Vashisht. In fact, these two stars are said to be, are advised to be watched, by a married couple when they get married for the first time, because of the fact that though the two stars, they revolve around each other. So how did they find out, this particular movement of two stars revolving around each other in spite of not having, such technology? Secondly, it is also said, I cannot comment upon the correctness of this statement, but it is said that if you read Hanuman Chalisa, there is one line which says, Jukta Sahastra Yojana Barbhanu, Lilyotai Madhuruphalachanu. So if you look at this, study this particular line, it says one yug is equal to 4.32 million years, and one sahastra is 1,000 years, and one yojan is 8 miles. So if you multiply all these three figures together, it comes up to 153.6 million kilometers, which is roughly the distance between the earth and the sun. And it was written by Tulsidas in the 16th century. So it is quite amazing to see that how our ancient, sages and others are able to come up with such figures, and they are able to solve so much mystery. So the space, so I think that as Indians, I don't say that it's in our genes to know, but I do think that we have the capacity to explore. We have the capacity to think beyond and you look outside the box rather than be confined to conventional things. So, saying these few words, I would like to, wish everyone, very explorative and innovative culture, thought process to take our space science ahead. With these few words, I thank each one of you and welcome each one of you to the celebration of the first National Space Day. Thank you so much.
Speak loudly. Today we have with us Professor Sri Kumar, who is the director of Manipal Institute of Center for Natural Sciences. After his MSc in IIT Bombay, he did his PhD at the University of New Hampshire, US. From 1989 to 1999, he worked at NASA Goddard Space Flight Center, US as a research scientist. In 1999, he returned to India and joined the ISRO Satellite Center, Bangalore. And he was there till 2013 as a division head and then a group director. From 2013 to 2018, he was the director of Indian Institute of Astrophysics. And from 2018 to 2022, he was first the director at the Office of Space Science Program and then Satish Dhawan Professor at the ISRO headquarters. As I said, he is now the director of Manipal Center for Natural Sciences, where he is building a strong physics and in particular an astrophysics group. His area of expertise spans a wide spectrum. His expertise is on the science of payload design and development, X-ray multi-layer optics, solar corona abundance, extragalactic gamma ray background, and many others. He has about 150 papers in refereed journals and has guided successfully 6 PhD students. It is our fortune that we have the opportunity to arrange for his talk on future prospects in space science research. Hi, Srikumar.
Are you able to see me?
Yes, yeah, please.
All right. I can begin?
Yes.
Well, thank you, Dr. Professor Seshadri, for the kind introduction, and to Delhi University and faculties and students for this warm welcome. Happy to be part of this National Space Day celebration. So in the limited time that we have, I thought I will give you a quick glimpses of where we are and where we think we should be heading. I'm no longer with ISRO, but nevertheless still involved in some of the discussions that happened there with regard to future programs. So I begin with this discussion on where we were in terms of in terms of very early exploration of space, which began robotically, primarily using machines to really explore the outer space. Remember, the space age is rather short. It's just been about 60 plus years. And with the explosive realization that the Soviets managed to put a Sputnik satellite in space, it kickstarted the effort to pursue space research, which was quickly followed by American Explorer satellites. And as in many of these cases, scientists were involved in the early experimentation, and Dr. Van Allen and his team quickly realized that the radiation, there is severe radiation out in space, to an extent that people really thought space is completely radioactive and maybe of concern for human presence. But very quickly, immediately after that, there were other experiments that were flown, not just in the vicinity of Earth alone, but even as far away as Venus. Mariner 2, 1962, quite an impressive feat to see that very quickly we started exploring the solar system. It's a flyby mission, just to, couldn't really create an orbiter, but they did a flyby mission around Venus. And then very soon, we had this very important and long-lasting missions of Pioneer 10 and 11, Voyager 1 and 2. Voyager 1 and 2 launched in 1976, when a PhD student at Caltech realized that there is a unique alignment of planets in the outer solar system that allows a spacecraft with minimal energy capacity to really explore outer solar system. And very quickly, the Jet Propulsion Laboratory put together this Voyager 1 and 2, which, as you know, even today survives and has actually been returning excellent results, including the fact that we see the edge of the solar influence of the planet of the solar system, called the heliopause. But these were also complemented with human space exploration. Almost immediately after the Sputnik, 4 years after Sputnik, the Soviets managed to have Yuri Gagarin up there in the late 60s. The big space competition between America and Russia, the Soviets, led to this Apollo landing. In the 70s, you had long-term presence of humans in space using a space lab called Skylab. Did fantastic work with regard to studies of the sun, etc., where human presence in a space environment for long periods actually was very helpful. Subsequently, there were evolutions of these space stations in the form of the Russian Mir space station, and currently the International Space Station, which has been pursuing a lot of research in many areas of sciences and technology, with the capacity for humans to go dock, come back, and spend as much as a whole year, sometimes in space. So both the robotic and human exploration programs go hand in hand, and often there's a debate regarding which of these would be appropriate given the limitation of the funding, including for India. And for a long time, we have been actually focusing primarily on robotic exploration. And now, very slowly, we are taking the first steps towards the human space exploration programs. This is the first photograph that was taken of the surface of the moon by a robotic mission, Luna 9, in February 1966. So quite a long time back, very grainy photographs. Here is a picture of the view of Earth from moon, again taken by Lunar Orbiter 1. They used photographic plates and they were processed on board, digitized, and then sent back to us. But that's the first time we got a picture of Earth from moon. Subsequently, as part of the Apollo 11 preparatory mission, there was an Apollo 8 mission that went around the moon. And as it came from behind, there was a photograph of the Earth taken. And this has been a major step in actually making us realize how beautiful our planet Earth is and how we need to do whatever is necessary to protect this delicate planet from further destruction. In the late 60s, the landing happened on the moon. This is the Eagle lander. It's a gigantic structure. This is many stories high. Some of you who may have visited the US Smithsonian Museum for Air and Space, you can see a replica kept there, and you can realize how big this lander is. And so the landing mission happened for a few years, and then it got too expensive, and the human exploration program of moon was sort of put on hold until a re-emergence in recent times. And even the exploration of the moon itself took a resurgence only in the late 90s with the Clementine mission. And that is around the time that we also got involved. For those skeptics who think we never went to the moon and it's all a fake, we'll have to tell them, please visit, and you'll see the footprints left by Neil Armstrong, undisturbed, still on the surface of the moon. The retroreflectors that Apollo astronauts left there, which we can actually observe by shining a laser onto it and getting a reflected signal back, is also a clear evidence of the fact that humans did make it to the moon. And India was not far away. Here is the final Apollo mission, which not only have humans there, they have rovers that could travel kilometers on the surface of the moon in the early 70s. So we as humans had made great strides in actually exploring a foreign world. And then we went into this quiet mode for a long time, largely economics driven. But subsequently, there have been many points on the moon shown in these blue dots here, where either humans or machines have actually managed to land, sometimes bring back soil samples with which we have been studying the moon. At the very bottom, you see roughly where Chandrayaan 3 landed a year ago. And that is close to the pole, and the pole has certain importance. And the importance arises from the fact that unlike Earth, which is tilted 23.5 degrees with respect to the orbital plane of the planets, the moon is nearly is not tilted very much, which then means when sunlight, when it goes around when moon rotates and revolves, the sunlight, which is sun is in the equatorial plane, sunlight often may not fall within the deep craters at the poles, north and the south poles. So they are shadowed permanently. They're called permanently shadowed regions of the moon. And so that is an important thing from the perspective of future explorations, because such dark, permanently shadowed regions are critical to potentially look for resources of water and ice. And as you can imagine, water is an important component for human exploration, both from hydrogen as well as an oxygen perspective. So there is a great renewed thrust to really look at the poles of the moon to search for water ice. So the connection to Earth and moon is deep. It really arises from the fact that both of them formed roughly 4.5 billion years ago in the early phase of the solar system formation. At a time when the planetary system was not stabilized, there were a lot of collisions happening between large bodies and the planets and moon. And these would lead to formation of craters. Here you can see the Lonar crater on Earth, others on Venus and Mars, and as well as on the moon. But however, unlike Earth, which has an atmosphere, wind, rain, and flowing waters, where a lot of the surface gets transformed very rapidly, moon with its airless body actually preserves much of this history. And so moon is a great place to go back to study the history of the early solar system formation. And these have very important implications for not just for a geologist, but also for those who study biology, wanting to ask this question, you know, when did life form on Earth and why so late? So these are important questions, and the moon's study of the moon actually gives you very important clues that allows you to answer such fundamental questions. Today, with the substantial mapping of the moon done from orbiters, we now have various details. You know, this is the near side of the moon that we can see from Earth. Remember, one face of the moon is tidally locked with Earth, so we are not able to see the other side, which we call as a far side. And to go to the far side, you really have to go behind the moon. But today we understand this. For example, it's a case of iron abundance taken from an earlier satellite. And we have details regarding the gravity, strength of gravity across the surface of the moon using test particles. And the test particle is actually 2 spacecrafts. They just simply measured the separation of spacecrafts as it went around the moon. And so now we have very detailed models of this gravity. And this is a very important input because, you know, when you have a spacecraft flying at 50 kilometers or 100 kilometers above the surface of the moon, you'd better understand the gravity very well. Otherwise, you know, there is a high probability that you use your spacecraft, it could crash onto the surface of the moon. The Chandrayaan missions that have been flown often require periodic corrections in their orbit. Otherwise, every 2 months, you'll actually see the orbit actually dipping down because the moon is not a perfect sphere. And so because of its non-sphericity, it gives us the perturbations that actually disturbs the orbit and actually can lead to decay of orbits. So those are important things, and knowledge of the gravity is very critical when in future, if you really want to fly a mission, say 10 kilometers above the surface of the moon, you really need to have very fine control on the local potentials critical to a spacecraft control. So the Earth-Moon system is an evolving system. Tidal interactions with our ocean and land actually ends up dissipating energy. But there is also angular momentum. And so the Earth actually slows down in the process, which means it loses some angular momentum that has been conserved. Moon actually takes that angular momentum. Moon is gaining angular momentum, and very slowly it's moving away from Earth at the rate of about 3.8 centimeters a year. The origin of Moon is sort of largely understood from the simulation that suggests a large body, almost as big as Mars, collided with the early Earth, knocked off a lot of the surface material, and then maybe a little bit of the core as well. And then it gravitated to form the moon rather quickly in a matter of days, is what the model seems to suggest. Now, these are important concepts on which we think moon is formed, and the key is to now test this. So what is the source of lunar data? Today, a lot of the data comes from samples of rocks and soils that have come from Apollo missions, the Soviet lunar missions. We have a small sample of this sitting at the Physical Research Laboratory in Ahmedabad, given to us by the Soviets. The Chinese Chang'e mission very recently brought back materials from multiple regions on the moon, and these are all taken and analyzed in great detail in the laboratories using very sophisticated tools to really tell us more about the moon. And so in addition to all of this, of course, you have rovers and landers that can do localized measurements and then remote sensing from an orbit. All of that put together, including ground telescopes. You know, the Arecibo, before the Arecibo radio telescope went down, it has been used extensively to study lunar craters. So a combination of all of this actually has been a primary source of information. And so meteorites are also major inputs, and these are all used to study the history of the moon as best as we can. And today, if you go to some other laboratories where long cores of soil have been brought back from the moon, many of them are still preserved in very pristine conditions, unopened. And that is done consciously to ensure that we preserve and keep it uncontaminated as and when very advanced instrumentation gets designed and made available for use. So NASA has actually kept a lot of this soil aside for those times when we will have even more sophisticated instruments to understand the texture, the composition, and many other details from these soil samples. Now, India has actually decided to get into this rather at a late stage. Right from the late 1990s, there have been Professor Narendra Bhandari from the Physical Research Laboratory has been a very persistent campaigner for a lunar mission, and he's been studying it. And after many, many years of struggle, effort, running around pillar to post, trying to say we must have a mission to the moon. Remember, this is a time when India also needs to justify utilizing resources for pure science studies as opposed to application-driven remote sensing programs and communication programs, which has been the thrust of the Indian Space Research Organization's activities. It was felt that the time has now come for a limited number of core science missions, and Chandrayaan-1 was sort of formulated in that framework in the same manner as how the astronomy satellite AstroSat was also conceived around the same time. So the focus of the lunar missions from India was to really look at the current problems at that time. And the problem there was in terms of asking, is there any evidence of water on the moon? Initial soil sample results, etc., showed very minimal, almost no presence. But late in the 90s, there was an effort to look at certain kind of rock samples, under which careful studies, they showed that deep inside these rocks, you could actually sample presence of water at some tens of parts per million. And that was a hint of the fact that maybe there's more water out there than we thought. So the experiments on the lunar mission Chandrayaan-1 was actually heavily focused on trying to ask this question about evidence for water. And we looked for evidence for water using infrared. This is a map from the infrared experiment that was actually contributed by Brown University and the Jet Propulsion Laboratory, which actually showed large-scale presence of water on the moon. And then there was also effort to look at the poles, and that is not easy to do with infrared because there's not much light falling on it, sunlight. So you use radar. So you actually use what is called a synthetic aperture radar. You actually bounce a radar beam, and the return of a radar beam can, in particular the polarization, can suggest the presence of water ice. Of course, there are other degeneracies in the signal, and so it has not been an easy thing to do. But these were experiments that were done to really look for possible water, and not because you're using low frequency radio at around 1.5 gigahertz or so, you can actually penetrate the soil a little bit and actually look for subsurface water ice. So the effort was also to look for these things. And then they look for minerals on the surface of the moon to understand composition. You look for chemistry. Chandrayaan-2 carries a very important experiment to do the first mapping of the chemistry of the moon. So you now have maps of the moon in iron, in titanium, in magnesium, aluminum, sulfur, calcium, and so on. So we now have that combination of data. We have imagery that actually tells you in great detail the presence of boulders, very critical when you're trying to land precisely. And so such data is used to understand. It's also very important to understand for geologists to understand what causes craters. Are there landfalls? What is the nature of the impactor that actually produces this crater? Can you see parts of the impactor itself? These are important questions, and you need high-resolution cameras. So this is actually one of the most highest resolution cameras ever flown to the moon on Chandrayaan-2, which can actually now see 25 centimeter size objects. This is an image, again, taken from the Chandrayaan-2 that actually shows the presence of the Apollo lander, Apollo 11 descent stage. There's a little bit of a shaded, there's a shadow from the moon, from the sun, which is on this side, showing the shadow of the descent stage of Apollo 11. So from 100 kilometers, you can actually see a lot of things on the surface of the moon. And since it's an undisturbed place, you could visit and revisit multiple times. Chandrayaan-3 a year ago was trying to land in this little square patch, rectangular patch, 2.5 kilometers by 4 kilometers. That's a fairly large section. Future demands on landing would talk about 100-meter square landing patches, and that is a challenge for us to do. And so that is precisely what we are supposed to. Just a quick shot. As it's descending, you can see a lot of lunar dust being blown away. Then finally we landed. And the first photographs on the surface showing the terrain actually is less dust than we anticipated, but it's clearly not a very smooth surface. It's really rock strewn. And then an image of the fact of the lander taken by the rover from near and then from far away. So that has been a very successful and important achievement. Remember, 4 years before that, we had tried to land, and it was a great disappointment. And so to all the scientists and engineers who were involved in doing this, it would have brought a tremendous sense of satisfaction, and to the nation as a whole, a sense of achievement. The question now is, what next? Where do we go beyond this? And that is, of course, the focus is going to be the South Pole, because of the arguments that I made earlier, that the pole is where a lot of the, we think, resources are there with regard to both water, oxygen, and hence oxygen and hydrogen. And there's another important reason. The moon has a lunar day is 14 Earth days long, followed by another 14 lunar night phase. And this night phase is of concern to our current powering systems. Our primary source of energy is still the sun, and we use solar panels to really power our systems. And for 14 days, if we do not have any power generation, we have serious concerns. The poles of the moon have often mountain tops where if you can in principle get sunlight for much longer periods of time. The sun goes around it, and you are able to actually capture sunlight for much longer periods of time. So the lunar pole is also seen as a better place to set up a station, because of the fact that power, access to power is much better compared to any other location at lower latitudes. But the pole has concerns, and the concern is because the sun is coming at a grazing angle, it's almost hugging the ground. It produces large shadows, great shadows. And here is a picture of this shadow of the South Pole. But then, it gets really bad if you start looking at how the shadow evolves. So this is showing the shadow changing from the 1st of January 2024 onwards. Almost every day is changing. And this is, imagine in such a situation, you have to land, and you better understand very well where the shadows are, and you have to precisely land in some location where there's both sunlight, so that your systems can be powered and so on. So it imposes a severe challenge with regard to South Pole landing. And it was also a concern when Chandrayaan-3 landed, because if we land with the panel of the lander not in an ideal position to actually power it, we would be, there would be serious consequences to the mission. So all of this puts a lot of demand on ensuring that we actually understand the environment in which we're walking into it, and then we have what is called precision landing capability that takes us to the right place. Now, in the remaining time, let me just have a quick run of our going beyond our solar system. Our solar system is heavily, as of now, driven by our own star, the sun, which is a complex ball of gas with magnetic fields. And we, as scientists, astronomers, have now learned to partially understand why sunspots on the sun evolve with time, why sun seems to have an 11-year cycle, and so on. And so that tells us something about how other stars are. And there are a large number of stars in the sky. Their sizes vary, their brightness vary, and the temperatures vary. And astronomers over the last 100 years have managed to put a story that could tell us why stars have a certain color and what their average lifetimes are, and so on. Stars are not stable systems. They form, they grow, they evolve into large stars, can evolve into red giants, undergo a supernova explosion, and could result in things like neutron stars and black holes. So these are evolving systems, and astronomers are always keen to study these systems. Some of this we can, of course, do from ground. Optical astronomers have been studying that for many centuries. But you understand that our atmosphere does not allow all the electromagnetic radiation to come through. In particular, it actually doesn't permit short wavelength radiation, ultraviolet, X-rays, gamma rays to come in. And so if you want to study these objects at these wavelengths, you really need to go outside the space, outside the atmosphere, and hence into using a space platform. Here is a picture in optical light showing a couple of galaxies out there. They look harmless. independent galaxies, living their lives, until I look at the same thing in radio, and I suddenly see that they're not just isolated galaxies, they're interacting galaxies. There's gas flowing from one to the other. They seem to have been interacting quite a bit. So the power of studying astrophysical systems using multiple wavelengths is very, very important to get the whole story. Here's an example of Centaurus A, the nearest active galaxy is not very far away. 13 million light years is a stone's throw away from us. Powerful galaxy. If you look on the sky, is many, many degrees wide. But if you see that in various wavelengths, again, I see completely different pictures. So studying any one of them wouldn't tell me the whole story. And the goal today of astronomers is to put all of that together to make a complete picture of what exactly is happening in such systems, what are the physics processes that are going on, and someday, who knows, some of these processes might be means by which humans might learn to extract energy. So India had a satellite called AstroSat, shown here in the clean room, launched in 2015 with the objective of actually studying the universe at multiple wavelengths. Here we use ultraviolet as well as low energy X-rays and high energy X-rays to study both galactic systems as well as extragalactic systems. Here's an example. On the left is an image from one of the ultraviolet imaging cameras on board. This is one of the sharpest ultraviolet camera with wide field that has been flown, and that shows the presence of a bright UV emitting nucleus of a galaxy. But alongside that, you also see little filamentary structure there, and another one here, which seems to have sort of knots along with it, as though there are places where more stars are forming. And today we understand this as something that arises from interaction of two galaxies. And the shock of the former interaction actually gives rise to the formation of material gets shocked into thin strands, and in those thin strands, new stars are forming. So it actually tells you a lot about that. So as AstroSat continues to do very well, and 8 years plus it's actually running. And here is a more recent satellite that was launched in the first of this year, ExpoSat, which actually takes another major step in actually looking at the universe, studying the universe in polarization of X-rays. X-rays are polarized, which means their electric field is actually sometimes confined to one plane, and that is suggestive of the presence of magnetic fields in astrophysical systems. This is one of the best ways to study magnetic fields in astrophysical systems, and this has been a major gap in our study over the years. There's been only some 3 or 4 polarimetric missions in X-rays, and so this is a major and important area of research, and we just started getting data from this mission. Now, we need to look at all of this in the context of the wider astronomy focus, and that is in terms of when you have, as I mentioned earlier, you can actually study astronomy at visible infrared from ground. We have major telescopes, including the 3.6 meter Devasal Optical Telescope in Nainital. And at extreme high energies of gamma rays, you can actually observe them from ground. In Hanley in Ladakh, you have this Department of Atomic Energy runs this facility called MACE, a 21 centimeter large diameter optics for studying tera-electron volt systems, very high energy systems. And these are complemented radio, and again from ground. We have Ooty Radio Telescope, the Gauri Biduni Radio Telescope, and the GMRT near Pune, very large low frequency interferometry system. And supplemented with space-based systems of AstroSat, ExpoSat, Aditya L1 studying solar, the sun, and its and then you have, as you look towards the future, a series of experiments that are being planned. Includes a large experiment to study ultraviolet spectroscopy. I mean, with AstroSat, we've done ultraviolet imaging, and the natural thing is to look at spectroscopy. And the imaging also is being improved. They're looking at an imaging that is comparable to the Hubble Space Telescope in ultraviolet. So at 0.2 arcsecond resolution imaging of the sky. There are also transient studies being planned using an experiment that has been proposed by the Indian Institute of IIT, led by the group at IIT Bombay. And then there are large experiments to study polarimetry across multiple brands of X-rays. A challenging mission. 10 years from now, we should have it there. And there are proposals also to look at planets outside the solar system. As you may all be aware of, there are planets outside the solar system, and these planets actually have we have actually looked at the composition of the atmosphere of these planets by using the light from the host star as it goes to the atmosphere of the planet as it goes in front of it, to study absorption features that will tell us about the composition of these atmospheric composition of these planets outside our solar system. These are also supported by the mega projects that are going on in India, the 30-meter telescope project, where India has a 10% role, the square kilometer array in radio, and of course, the LIGO India gravitational wave observatory. So there's a large set of facilities, and students, those who are thinking about pursuit of research in this area can actually see this collection of facilities, and your challenge would be to find interesting problems that makes use of these facilities to really address and understand the science behind many things that are going on in nature. Now, it's important for us to really keep an eye on the fact that we are in a Milky Way galaxy with the sun positioned very far from the center of this galaxy. Nothing special about this galaxy, location of the sun. But there are 100 billion stars. Many more things can actually happen. And the goal is to really understand and study some of these potential planetary systems around such stars. So this is an expanding area of research. The sun itself, when you look at habitation, we take our own solar system and we see that our own Earth is actually heavily driven by activities of the sun. The sun has a powerful solar wind that is constantly blowing out, and it enters the Earth's poles because Earth we are shielded by Earth's magnetic field, but the poles are vulnerable, and we actually see beautiful aurorae as a result of particle interaction in the upper atmosphere of Earth. But the sun is not a steady object. It varies a lot. And here is a cycle, nearly 400 years of sunspot observations that show that while it has this 11-year cycle of maximum number of sunspots, it also shows periods of hardly any activity. These are important concerns in the context of long-term sustenance of life on Earth and so on. And at short intervals of time, they show explosive behavior because of solar activities. And these are critical because such activities throw out a large amount of material into the solar system. And that means also affecting Earth. And so when you're searching for absorption features in exoplanets, one needs to also study the nature of the host star that is actually driving it. And these are important questions that need to be addressed when we talk about habitability. Are we going to find Earth 2.0? It will depend not just on the fact that it is at the right temperature, but it may be around a star that is very violent in terms of its activity. And then it may or may not be in a position to support life on such systems. So these are important questions for the future. Looking our own near Earth space, when we explore when the effect of the solar activity on the human presence in the near Earth system, or on Mars, or on Moon, humans have to go there. They have to worry about the fact that all of this radiation also produces biological effects. And the effect of radiation on biology is often sometimes given by something called the weight factor. If the photon, that is a gamma ray photon, has a weight factor of 1, and electrons are also roughly the same, but neutrons, which are neutral particles, and they come from the sun, and because they're not charged particles, they actually can penetrate quite a bit. And since our body is has a large fraction of water, and water means hydrogen, and so hydrogen, a proton and a neutron are very similar, so they act like billiard balls. They actually bounce around a lot, cause a lot of damage. So the biological damage from neutrons is very large. Neutrons are not easy to detect. So this is a challenge, and that is some of the things that some of us are now working on, how to design neutron detectors that will tell us the damage level, tell us about the spectrum of neutrons, what is the energy spectrum of neutrons coming from the sun, energy spectrum of neutrons producing inside, a space station. The walls of the space station produce neutrons as secondary particles. When protons strike the outer surface, it actually produces neutrons. About 1/4 of the radiation inside a space station comes from secondary particles. So that is of concern. So these are important things that we need to pay attention to as we look at it, because we are also around Earth is very strong trapped radiation belts. Earth's dipolar magnetic field naturally lends to the trapping of charged particles. These radiation belts, the size of this grows and shrinks depending on the activity of the moon or the sun. And so if tomorrow you want to really take off and go to the moon, you have to cut through these radiation belts. That's a very, very risky proposition, which is why often you have a very powerful rocket, you'll say, all right, in one go, I'm going to cut through the radiation belts and not go around it multiple times. When we design payloads on Chandrayaan missions, we often have to account for the fact that it goes through multiple transits through the radiation belts, and where much of the radiation damage to experiments happen. And so, but with humans, we don't want to do that. We should be like to cut through straight. And you want to do it at a time when the belts are very thin, when the energy of the particles are appropriate and so on. So that's an important part when you look at human exploration of the moon. I want to close with this one slide. This is a very famous 1927 Solvay conference, where at a time when quantum mechanics in physics was actually at its peak with regard to radical revolutions taking place. Almost every day you see results emerging from these things. And you may not be able to see the names of picture, but Schrodinger, Albert Einstein, Lorentz, Madame Curie, Max Planck, Dirac, Debye, a whole host of them. 29 of the 29 participants, 17 either won the Nobel Prize or got the Nobel Prize a little later. It's a very important meeting. 100 years later, almost 97 years today, now, we look at it and say quantum mechanics had moved away from just the esoteric or the confines of the discussions amongst a handful of scientists to an area with tremendous applications that many of you don't even realize you're using with regard to all the sophisticated technology we now use, whether it be from anticipated computing capabilities from quantum computers, secure communication from quantum communication systems, and so on. So, even the application of relativity for your GPS systems, which are every day being used when you order your food through Swiggy, are all coming because of the the application of fundamental sciences to technologies. 100 years from now, one can only imagine what the nature of that would be with regard to current technologies of today, and in particular in the context of space exploration. And many of you in the audience, the youngsters, you are in a position to actually be part of it, get involved. And so I wish you the very best. And thank you.
Thanks a lot, Professor Srikumar. It was an excellent talk, and I'm sure especially students would have really enjoyed it. Thanks a lot. Thank you very much. Would you like to take some questions?
I can if there are questions.
Yes. Yeah. No. No question.
So you can just stand here, close to the screen.
I think it was a wonderful talk.
Thank you.
So I was just, curious, looking at the samples which were collected by Apollo mission, Luna mission, and subsequent. And what I see, the earlier missions were very successful in bringing a lot of samples, but then subsequently this has decreased. Any particular reason, or it's only the costing?
No, clearly the Apollo missions were tremendously well-funded because politics was involved. And then the politics vanished and the money, there were actually 20 Apollo missions, but only 17 they decided, let's scrap it because money is going to run out. That's the prime reason. Of course, there was also a phase of explosive R&D activities. Even today, I find it very hard to comprehend how they managed to pull all of this off in such a short time from where they began. That's why I said, when in 4 years, if humans could be sent into space after the first Sputnik launch, someone could ask, why are we taking so much more time? And I think many factors are involved. So it's not that there's a technology limitation. It's a question of actually putting in that kind of focus and that kind of funding and that dedication with which people work then. But today we have other responsibilities, so we can only handle it at a certain measured level. So it's just only a matter of time. And so that's the only real reason. Yeah.
Thanks. Okay, Sri Kumar, thanks a lot. Thank you very much.
Thanks very much. Yeah. Wish you the best.
Yeah. Take over. My talk has to be. No, but it has to come here. No? I can't send it. No. My talk is there after that.
It was a fantastic session. Can you hear me? Yes. Great. So now the biggest attraction of today is celebration of Space Day. Let me introduce, and I take the privilege to introduce Professor B.R. Seshadri from Department of Physics and Astrophysics. Also, Professor Dhrupjyoti is the head of the department. Please. And also is the dean, the Faculty of Sciences. And it's a fantastic day, and maybe most of you may not have connected with what I have just explained, but you may take little time to understand what all technologies put together is making. And I'm personally very excited to look forward to the successful launch of Gaganyaan, which is going to happen next year, I believe, 25, right? So I think he's a dear friend, and he's popularly known as Sesh. Because I can't pronounce his complete name, T.R. Seshadri.
Terendu Rajgopalan Seshadri Ayappa.
So we always call him Sesh, right?
That's the new name.
So anyway, so he's a cosmologist, and I think he's going to guide your brain and make some idea that how whatever you are studying here in Faculty of Technology can contribute something in the domain of astrophysics, physics, and how you can collaborate even in the during your BTech program, or you may reach out to him or any other faculty member to conceptualize some small project to understand the nuances of this. So this is fantastic, and I welcome Shay to
Can you have a slide?
I think it will be better if we have this.
Really? Yes, I can. I know. Michael Jackson. So yeah, that's good. Can you make it? I mean, why is only half of it? Oh, I see. Okay. It's a PDF. But I mean, fitting the screen, fit the screen, right? It's full screen. What is it? Yevala. This is like a homogeneous universe. I'm sorry, I'm technologically challenged.
That is because of the topic. You said surprises from the sky, so it's surprises from the technology.
It's more of a shock than a surprise. That's better. Okay, Hari. So after that excellent talk, I think this is going to be an anticlimax, but nevertheless, I will venture to give this talk. So, I have given some topics in earlier talks, so if somebody already knows that topic, just keep quiet. Okay. So I will talk about 3 surprises from from the sky. One is I call the strange behavior of the orbit of Uranus. The other is something called the story of delta C5 variables, and I will explain to you what I mean. And nuclear explosions from where. Okay, and as we go along, I will reveal what it means. How do I change it?
Next. Right.
Okay. Okay, so let me first talk about the strange behavior of the orbit of Uranus. So now, one must have known from school physics that the orbit of planets is roughly circular around the sun. Now, if the planet is going circular, the velocity direction will of course change with time, but the speed will remain same. So, as a planet goes around the orbit, you expect that it will be moving with the same speed. However, when they observed Uranus, they got a surprise. They found that in some regions, it was moving with a higher speed than as compared to some other region, although it was still going around in a circle. The only way they could comprehend this was to assume a heavy object here, so that when it is coming here, it is being pulled and the velocity increases, and as it is going here, it is pulled back and the velocity decreases. And soon enough, they found that that it is because of another planet called Neptune. So Neptune planet was actually predicted and then discovered as a surprise. So basically, since Uranus orbit is smaller than that of Neptune, the Uranus goes around the sun at a faster rate than Neptune. As a result, when Uranus is here, Neptune is here, so it is pulled along the direction of motion, so the speed increases. When the Uranus has reached here, Neptune has reached only here, and it is pulled back and slowed down. So this is the first surprise which I want to tell you, that they didn't expect that there will be a planet, but because of the motion of Uranus, they guessed and later found, observationally it was found later, that indeed there is a planet called Neptune. So it was a prediction which was confirmed by observation. Okay, the next surprise I want to tell you is what is called the delta C5 star. So I will not go into the technical details much, but I will give you just the basic results of this. There are, okay, so when you have a lioness which has given birth to cubs, you call the strongest one as alpha, the next one as beta, and so on. So similarly, when you have a constellation of stars, then the brightest star is called alpha, the next bright is called beta, and the fourth brightest is called delta. So in the C5 constellation of stars, the fourth brightest star had a very strange behavior. And the behavior was that its brightness was not constant, unlike usual stars. The brightness was varying with time, but in a very regular fashion. And often in astronomy, you only talk about time scales which are million years or billion years. But here is a thing where it changes in a matter of 5.4 days. Then, Henrietta Leavitt, this is an example of many women astronomers who were either not recognized or recognized much later. Now, she was working as something called a computer. You had lecturers, readers, professors. Like that, those days, there was a position called computer, and the work of that person was to do exactly what the computers do. Sanjeev will be very happy about the computer, okay? So this was a position. So this was to basically do calculations for senior astronomers. And what she found was there are a whole set of stars which have this behavior. And what she found was the time period with which it varies is related to how bright it is. And from here, one could predict, seeing the time period of variation, how bright is the star, and hence how far is it. Now, this had a very deep implication. So the time period was proportional to luminosity, and for the first time, we had a yardstick to measure distances in cosmos. Otherwise, we could only measure distances to nearby stars. Using this yardstick of Henry Limit, the famous astronomer Hubble found an interesting thing. You know, there is something called a nebula. Nebula means a fuzzy object in the sky. It just looks like a cloud, but while the other clouds go away, this thing remains there in the sky. So you know that it's a part of the universe and not just the atmosphere. What they found was there is a particular nebula in which there are these variable stars. And using Henry-Leavitt's method, they found the distance to the star. And that is where a major surprise was hiding. And this was not the idea. Again, this was a complete surprise, and they had not even thought about it in the wildest imagination. The distance to this nebula happened to be much more than the known size of our galaxy. For the first time, they realized that the universe is more than just our galaxy, and the whole subject of extragalactic astronomy was born. Okay, and this nebula, which is just a fuzzy patch as seen by Hubble, is what we today know is a galaxy in its own right. It's 3 times heavier than our own galaxy, and it is the famous Andromeda galaxy. The third and the last one, which I will mention, is what I call nuclear explosions from where, and that has actually more to do with the Space Day celebration because it has actually to do with satellite observations. You see, before, I mean, this is for all the young students who may not have known the era of communist Russia. Okay, so before the perestroika of Gorbachev came, Russia had a communist system, and there was always a Cold War between US and what was called USSR. Okay, the Russian Federation, which is now. Okay? Now, there was this nuclear arms race going, and they were all testing nuclear weapons. At some stage, they decided to come to an agreement to limit the nuclear tests. So they decided that they will have a monitoring of each other's facilities so that they are sure that the other person is not doing nuclear tests and violating this agreement. But there was a problem. Those days, Russia, the then USSR, was much more advanced in space program. As Sri Kumar himself said, the first satellite was launched was Sputnik by Russians in 1957. Okay, and they were very advanced. And what US suspected was that, he was also mentioning that moon is tidally locked, which means we always see only one side of the moon. What US suspected was maybe USSR is sending rockets going to the other side of the moon and testing their nuclear weapons there, and they won't be able to see it. And this was a major concern for them. Okay, so what they did was USA launched a set of satellites called Vela satellites, and you could monitor from a very great height above the Earth. There were 2 advantages. One is at such a great height away from the atmosphere, the noise level is low. And the second more important thing was it could peep into the other side of the moon. So the moment there's an explosion, there will be a mushroom formation and they could see it. July 2nd, 1967, at this time, Vela 4 and Vela 3 satellites actually saw a flash of gamma ray. Okay? And the immediate thing was they were in fact right, and the Russians are conducting nuclear tests on the other side of the moon. But there was a problem. A nuclear explosion has got a certain definitive signal. This was not like that. For nuclear bombs or the nuclear test, first there is an intense burst of gamma ray when the actual explosion takes place. And all the radioactive unstable nuclei starts decaying, and then there is a decay, the radiation due to decay. None of these features were present. Instead, all these features had another signal. There were actually two distinct peaks of radiation burst. Usually, such a thing happens when there is a solar flare, like for example, what Sri Kumar was telling, material being thrown out of the sun, or when there is what is called a supernova explosion, which is the end star or end stage of a dying star when it just explodes. They checked the records, none of them had occurred that way. So they were skeptical about it, what is happening. But the source was unlikely to be nuclear explosion because those signals were not there. So they had actually filed away the data for later investigation. In 1969, the next Vela satellite detected 12 such signals. And now definitely you realize, okay, another thing was, they then realized that the signal was not coming from the Earth or from the moon, but from outer space. And they were sort of high energy phenomena, but not this kind of nuclear explosions. What they were seeing was one of the most energetic phenomena in the universe called a gamma ray burst. And today, gamma ray burst is a very active area of research in astrophysics, and we still do not know their origin properly. And this is how the existence of gamma ray burst was detected. Once again, never anticipated. We're trying to look for nuclear explosion on the Earth, and they happen to see something in space. I'll just conclude by one important remark. In fact, two important remarks. One of them, especially for students, is that one might think that anyone could make a discovery and something important will come if you have luck. It's not true. Why is it not true? Yes, luck can play an important role. But all those people who did the discoveries and were lucky had already done enough work to interpret what the surprise which the nature was giving. So it is something like this, that if you are farming, of course you have to be lucky to have rain. But you have to dig ponds to collect the water, as when it rains to collect the water. So it is just not whether it rains or not, it's purely like luck. When nature showers luck on you, you should be ready to receive it. So I will just stop with this, except I will just make one comment. Since it is Faculty of Technology, there's a lot of people from technology. You see, often one thinks that space research, you think of physics. Not completely correct. You see, you consider all this Apollo mission. The physics or chemistry comes only after you land and you pick up the material and you are analyzing. The rest of it is engineering. Okay, you need excellent engineers. In fact, if you go to ISRO, engineers are in great demand. You have to make, the vehicles to take the satellite. You have to have good electronics. And many a time, this electronics is of a new kind because the situation which exists in space is very different from the situation on Earth. So you have to discover new kinds of materials. And I think this is something which students should take care of. Thank you.
I request Srika Technologies, the program party to say a few words.
Thank you, Professor Priya Samariji. You are doing a good job. It is very interesting.
As long as you don't stop
Today we are scientific that is International Space Day. And it is the beauty of our country that the brilliant minds of our country, particularly I think Professor Samariji told that engineers, they are doing the wonders. So you can do the wonders because when we are ISRO, many people around 70% they are engineers, physics, chemistry, and so we can do logistics for the beauty is that any country can send the space. That is the success of the that is because it's less amount of money and the indigenous engineering. That is the beauty of our about anything which whatever we are doing the space research. Yes, we have the money. It's very less in comparison to any development. In comparison to ASR because only the engineering systems they have right first type of success. So if you do that, if you do the research in that field, and you can achieve, we can do wonders with the Indians have the great minds, and we will achieve all these things, and we all be marketing
Thanks for I think I was expecting Dr. Vanita to give the vote of thanks, but I thought let me take the opportunity because of the fact that I have to thank two people for the for holding this National Space Day at a very short period of time. So my thanks to Professor Sanjeev and the entire Faculty of Technology team for giving the support and facilitating the organization of this National Space Day. So a big round of applause for I would like to thank
Some science has begun.
Science.
Has begun also.
So our keynote speaker for today, Dr. Sri Kumar. In fact, it was just 2-3 days back when I contacted him because I got his contact details from Professor H.P. Singh. He told me to contact him, and I was quite apprehensive whether he would agree to deliver a speech at such a short notice. And when I called him up, he readily agreed. So thanks to him for accepting our invitation and for delivering such an insightful talk, right from taking us through the the whole history and evolution of space science, how humans have began the space research and how far we have reached, and at the end motivating all our students regarding the future research that they can do and they can add on. My special thanks to Professor Seshadri for accepting the responsibility of contacting Professor Sri Kumar as well as giving a very interesting talk. As usual, he is a very humorous person and we enjoyed listening to you and the surprises that you have given. And the one thing which I think which every one of you can pick up, all my students, their students, is that it is you who is going to matter. How anything from India is taken to space and to planets and other areas of the universe, because you are the ones who will, take you'll be discovering or making, not discovering, actually inventing the equipments and the technology, build the technologies to reach there and decipher new things which are existing but still a mystery right now. So wish you all the very best, and I thank Sir Balaram Pani, our Dean of Colleges. Sir has been very kind to accept our invitation, that was a very short notice. Sir हमेशा जब भी हम approach करते हैं किसी भी program के लिए, अगर कोई prior engagement नहीं है, he never says no. So let's give a big clap to कभी ना नहीं हो, जब भी मैं आपको approach करती हूँ. So I feel privileged to work with sir.
You should take advantage of what you asked.
And I thank our CEO IOE Professor Rajiv Gupta ji. Sir को मैंने कल ही बोला sir आप आइएगा. So sir thank you. कनाड भवन को आपके IOE और FOT से ही जाना जाता है. तो आप इनके लेवल पे होस्ट कर रहे हैं, and thank you for gracing this occasion. I thank the Faculty of Science. Sir had a PhD presentation. And he said, I can come and join just for a few minutes, but he stayed throughout the program, so that means it was a very interesting program. Thank you for raising the occasion. I thank Mr. Tandon, Professor Garita, entire faculty of technology. Since morning, sir has been raising these two events, morning event and afternoon event. Thank you so very much.